Hey guys, I'm going to do one more quick lecture for you today, and this is going to be about percent composition, which is another topic that will be covered in the book this week. So I'm going to go ahead and share the screen and pull up one other document, and we're going to walk through how you solve a percent composition problem. Okay, so here's an example for you. And the whole idea about percent composition is that you have been given some percents of substances within a compound, right? And so what you're trying to figure out is what's the empirical formula. Now, again, remember, our empirical formula is just a ratio. So it's the ratio of one atom to another atom in a chemical formula, or one to several atoms, right? So let's look at the example and walk through it a little bit. So we've got a percent composition, and we've been told that the compound contains 50.05% sulfur and 49.95% oxygen by weight. And the first question you're asked is, what is its empirical formula? There's actually two things we're going to figure out. First, we're going to figure out its empirical formula, and then we're going to figure out its molecular formula. So let's start by walking through how we do that. Now, you have not been told how much in grams you have of each of these two substances. You've just been told the percents of them. So the easiest way to figure out what the empirical formula is to assume that you have exactly 100 grams of that substance. Okay, now you could pick any number, but the easiest way to do it is just assume that you have that you have 100 grams of that substance. So if we have 100 grams of that substance, oh, actually, before we do that, let's talk about in general. Yeah, okay, that's the first thing we're gonna do. Assume we have 100 grams of the substance. Then after we do that, what we can do is we can determine the number of moles of each substance, right? Because if we have grams of each thing, then we can figure out moles of each thing. And once we determine the moles of each substance, we can compare the ratio of moles, and that will tell us our empirical formula. So that's what we're going to do. So we're going to start again. Here's the first step, by assuming we have 100 grams. So then if we have 100 grams of this substance, that means we have 50.05 grams of sulfur and 49.95 grams of oxygen, right? Again, they add back up to 100 perfectly, and that matches the percent composition that we were given, okay? Now, then what we have to do is we have to figure out how many moles each of these substances in grams represent, right? We're just going to use the molar masses, and we're going to turn each of one of these amounts, these masses via grams, into moles. So let's do that. So if we have 50.05 grams of sulfur, we know that for every 1 mole of sulfur, we have to have 32.06 grams of sulfur. So that means we have 1.561 moles of sulfur, okay? Let's look at oxygen. If we have 49.95 grams of oxygen, then for every 1 mole of oxygen, we have 16.00 grams. Now again, we're looking for just single atoms of oxygen. It's not O2 like the element. We're just looking for how many single atoms of oxygen we have, right? So that means we have 16.00, and we end up with 3.122 moles of oxygen. So we've got 3.122 moles of oxygen, 1.561 moles of sulfur. Now we've got to compare those ratios. Let's go on down here. We're always going to put a larger number on top, which happens to be oxygen for this problem. So the ratio of that looks like this. The ratio of oxygen to sulfur is 3.122 moles to 1.561 moles, and that gives us an even ratio of 2.00. So what does that tell us? Well, that tells us for every 1 sulfur, we have 2 oxygen atoms. And that would give us an empirical formula of SO2. Pretty straightforward, right? Now, the second part of this problem said if the molecular mass was 64.07 AMUs, what would be the molecular formula? Well, again, what is the molecular mass? The molecular mass tells us the mass of an actual molecule. So if we can determine the mass of the empirical formula, then we can compare that to the mass of the molecular formula and see what kind of multiplier we have. So let's go ahead and do that. So let's change our AMUs of the molecular formula to grams to determine the molar mass. So we know if the molecular mass is in AMUs is 64.07, the molecular mass in grams would be 64.07. Okay, so that's our molecular mass, molar mass, right? So it's the mass of 1 mole actually that would be the molar mass, right? Of 1 mole of that substance, right? So that's 64.07 grams. Well, what would the empirical mass of SO2 be? Well, let's figure that out. For sulfur, 1 times 32.06 grams. For oxygen, 2 times 16. So when we multiply those, add them up, we get that the molar mass of the empirical formula would be 64.06 grams. So again, we've got the molar mass up here of the molecular formula, 64.07 grams. The molar mass of the empirical formula, 64.06 grams. We're going to do a ratio of those. We'll divide our molecular mass by the empirical mass to determine the ratio. And when we do that, we get 1.000. That tells us, what does that tell us? It tells us that the mass of the molecular formula is exactly the same as the mass of the empirical formula. So what does it tell us? It tells us that SO2 is both the empirical formula and the molecular formula. Now, obviously, if we had gotten a ratio like 2 or 3 or 4, we would then multiply each atom in the chemical formula by that ratio. But that's how you do a percent composition problem. So hopefully that's helpful. And I'm going to stop the share for now, and I will see you later.